Section 5.2 talks about volumes of revolution. We use what's known as the disk or the washer method to find the volume of a prism. What a prism is, it is a three-dimensional solid in which anywhere you cut parallel to the base, you get the base. So if you cut right there parallel to the base, you get the same area as the base. That's called a prism. What would not be a prism would be like a pyramid or a cone, where if you cut in one piece or you cut in a different position, not piece, you will get an area, but it's not equal to the area of the base. So we're dealing with a prism here, and we know that the volume of a prism is always area of the base times the height. So here, if this is area of the base times the height, well here the base is a circle, so that's pi r squared h. Here, if this is length, this is width, the base is length times width times height. Here again, volume is area of the base times the height. Some books call that b, and in this case it's 1/2. If you call this side a, this side b, it's 1/2 ab times h. Here it's the same as this, since it is a prism. Area of the base is pi r squared times the height. Here it depends whether those are equal or not. Here I would say the volume will be v1 plus v2 plus v3. v1 will be a1 times its height plus base 2, area of that base, times its height. And if I figure out this volume, that will be area 3 plus its height. Of course, if these are the same, then I could combine them, and that will be equivalent to this. So now I'm going to take a specific area. Let's say I take y equal f of x. Oops, I want it to be a bit smoother. And I take this area from A to B. So we're talking about this specific region. So this is an area. And if I rotate that about the x-axis, what would happen? It'll create an identical copy that would look something like this, and it'll generate the following solid. Now if I want to find the volume for this, I'll take this from A to B, I'll call this x sub 0, and I'll break this. I always go to the original, by the way, always the original. So if I take this and I break it, this is x sub 1, this is x sub 2, this is x sub 3, x sub 4, all the way to x sub n. And what I notice, as this rotates, if I stake this and I break it, I'll say the volume of this will be, and we know it's tilted like that, it's not straight, so it's not like this. And assume that's v1, and I'll go to the next piece. As this rotates, if I cut this right here, so this first width is delta x, assuming those are all the same, this is delta x. Here again, if I picture this second piece, it would look like this. So it could be curved in or out depending on f of x. And if I look at the third piece, And of course, I could run this all the way down till the last piece. And the last piece looks like this somewhat. But I do notice that the actual volume is going to be roughly, and the reason I say roughly, I'm going to say area of the base times the height. So the reason I'm saying it's roughly, I know this is not straight. This is a bit curved in. So the height is not really as simple as this. But for now, assume it is close enough. So area of the base right there, right, times the height. Area of the base right there times the height. Area of the base right there times the height. Area of the base of the last times the height. So if I really look closely, I could write this two ways, and I'm going to do it both ways. I could say this is going to equal a of x1 delta x, because that right there is represented by x sub 1. That would be this first height. Plus the second piece, that radius right there is really that distance right there. That will be a of x sub 2 delta x. And for the third piece, that right there is really that right there. And that's a of x sub 3 delta x. And for the last piece, that right there is that radius, which is x sub n delta x. So two ways of representing this. One way is for me to say, well, you know, but volume is going to be the series I equal 1 to n of a x sub I delta x. And if I wanted to find the exact volume, I simply take the limit as n approaches infinity of that series. And that would be the integral from a to b of the area of x delta x. And notice that approximation becomes equal if you fit an infinite amount of subintervals there. Well, also, I could have said, instead of doing all of that, I could have said, well, look, isn't the area of this isn't that radius right there, the first one, isn't that f of x sub 1, instead of calling it the area, and then isn't that right there, isn't that height f of x sub 2, and isn't the third height, and that will be, let's say, that one right there, but up here, isn't that f of x sub 3? And isn't that volume the integral from a to b of area of the base? Well, isn't that base a circle? Can't I say that's pi? But r, isn't r f of x squared dx? Dx is the width. So think about it for a sec. If I look at that circle, that radius right there is actually that height right there. And that's f of x sub 1. So the area of that is pi times f of x sub 1 squared. When I look at this piece, and I look at that circle, isn't that radius, so it's pi times the radius squared, isn't that radius actually f of x sub 2? So two ways of doing this. Either you say, you know what, it's f of x squared, or you simply say the area of that disk. And here's what I just said written in a definition. Given y equal f of x is a continuous function between x equal a and b, if f of x is rotated about the x-axis and a thin cross-sectional area, that's these small pieces that I took, is chosen, a of x, where a of x is perpendicular to the axis of rotation. That's going to be very important how we pick those. There are two ways of doing those. In this section, we pick them perpendicular to the axis of rotation. Then the volume of the solid generated, well, this is called the disk method, because every time you rotate, you're going to be looking at a bunch of those disks. And all what you have to do is find the area of that, and that's pretty much does it. So now we're going to do this for two cases. Case 1, assuming there's no gap. Find the volume of the solid obtained by rotating the region bounded by the given curve about the specified line. Sketch the region as solid, a typical disk. Washer is coming up after. Now we're going to do the disk method. So if I look at this, and I'm going to elaborate on what we just saw, in case you don't see it still. If I take y equal 1 over x, y equals 0, x equal 1, and x equal 3. So we're talking about this specific area. I'm going to rotate this about the x-axis, so this is irrelevant. And I'm really looking at, as this rotates, it's going to create an identical piece like it, and it's going to look something like this. And I'm looking for this volume. So all what I have to do, I'm going to say volume is the integral, and this is 1 to 3. I'm going to pick my rectangles perpendicular to the axis of rotation. That makes this delta x. So all what I have to do is look at that one disk. I'm going to say that's from 1 to 3. So if you want to use the area of x dx, you can. And if you want to jump straight and use this, you can. But it helps to see it, especially when it's a washer. If I take this one piece as it's rotating and I turn it, I notice that it is a circle. And the radius of the circle is really that right there. And that is 1 over x. And the area of this circle is pi times the radius squared. So the book is not wrong in saying either or, times the thickness delta x. I'm going to set up the integrals assuming you know how to work them out. So this is x to the negative 2, add 1 to the power, divide by that, and proceed. So that's how we're going to do these problems. Now I'm going to set up the second problem. Y equal the square root of 4 minus x squared. That's the upper half of a circle. Y equals 0. I'm going to run this between x equal 1 and x equal 2. X equal 1. Oh, okay, let me adjust that. I just made these problems up, so this is not matching. Let me make that simply 9. There we go, much better. So this is a circle with a radius of 3. I do want to point out you could have overlaps. We avoid those in this class. So between 1 and 2. So I'm taking this piece of the circle. I'm going to rotate that about the x-axis. What's going to happen? it's going to create an identical piece like it right there. And I'm trying to find the volume for this now. Again, we're going to always use the original. So if I pick my rectangle right there to the original, perpendicular to the axis of rotation, I notice that the circle has the outer rim being the blue function. So this radius of that circle is actually the function itself, which is square root of 9 minus x squared. And the area of this is simply, so you could say volume is the integral from 1 to 2 of the area, oh boy, from 1 to 2 of that area dx. Or simply 1 to 2, well, the area of this is pi times the radius squared dx, and the radius happen to be simply nothing more than the function itself. So if it's not a washer, it's really easy to get. And if you square this and integrate, that should find you that area, that volume, sorry. Next problem. X equal y squared x equal y squared. Let's color code those. That looks like this. X equals 0 and y equal 2. We're talking about this region. So we really don't need this. That's part of the graph, that's not needed. And I'm going to rotate this about the y-axis. So do we agree that that's going to create an identical piece like it right there? And it's going to occupy all of that volume. As this rotates, I'm going to pick my rectangle, and I always pick it perpendicular to the axis of rotation. So that's a delta y in this case. And the disk is right there. I'm going to take that disk and draw it right there. And isn't that distance really just, this is x equal y squared? Isn't that just y squared? Can't I say the volume is the integral? And this is with respect to y because I picked it perpendicular to the y-axis from y equal 0 to y equal 2 of a of y in this case. And isn't that the integral from 0 to 2? And the area of this pretty much is pi times the radius squared dy. And there it is. You could do it in terms of x, you could do it in terms of y. It always gives you the same volume. Normally one direction is easier than the other, but that's not always the case. Now, what happens if I'm looking, and I'm going to color code those again. Let's say I have y equal f of x, and I have another function, let's say g of x. It doesn't have to match. Let's say if I take that piece, so that area right there, if I rotate this about the x-axis, what would happen? Do we see that? Not that sharp, but you get the point. And underneath that is kind of like this. So do we see that? That's going to create a piece like it. And as this rotates, there's a gap. It's hollow on the inside. I could fit my hand in there. There's a gap in this. Now, if I take one of those slices perpendicular to the axis of rotation, let me use black. If I pick my perpendicular to the axis of rotation, which is this, the x-axis, that's a delta x. Well, volume is going to be the integral, and let's look at how this is going to be. Now, let's pay attention to the details. Visualizing this is very useful. Oops, that's not what I... Oh boy. There. Now, do we agree that this is the actual area that I want? It's hollow on the inside. The actual x-axis is that point right there. Do we see that the radius, that is f of x, and the area for the whole thing is pi times the radius squared? But I don't want the whole thing. Do we agree that this hollow part is this part, and that is y equal, that distance is y equal g of x? I would take away that area, and that will give me the desired area. And if I factor out a pi, it's nothing more than the outer radius, which is the top, minus the inner radius, which is the bottom. So be careful not to do this. And that's a common mistake students do. Students say pi into f of x minus g of x squared. It doesn't work that way. So here I could say volume equal the integral, calling this a, calling this b, from a to b, of simply pi times f of x minus g of x dx. So it's important to graph this or look visually to figure out what the outer radius is and what the inner radius is, and that's simply, there's no pi there, right? Area that out. And if I go in and say that, well, if you really use the circle part, that's what it looks like. So now let's look at some of those. So visually, I'm going to use colors to color code the outer and the inner so we could visually see that. So here,